Okay. Oh, just one other to go in the room. Okay. So hello everyone. Welcome to this workshop dedicated to Uvex by Shelyak. This workshop will be led by François Cochard, and we have planned this workshop today because the 16 Uvex of the pre-series will be sent soon now. So it's just to present you this new Uvex by Shelyak. And you will therefore discover what this Uvex look like. And I have time also to show some Uvex process with Demetra software. Another people coming, so sorry. Up. So you can also answer your question if you have some question. And please put your microphone off to not interfere with the speaker. And of course, you can put on your microphone for asking questions or ask them via the Zoom chat accessible at the bottom of your screen of your Zoom interface. We will record this workshop, and after we will put the video. Sorry, I have to admit another people here. Okay, we will put the video on the Shelyak YouTube channel after. So now I leave the floor to François, who will tell us everything about Uvex. So stay with us.
Well, everything. I don't know if I will be able to say everything, but this is a real pleasure again to talk to you. I'm always impressed by so many people from so many locations, countries in the world, and really that's great. We as Olivier said at the beginning, we planned this meeting mainly for people who participate to the first series of the first run of Uvex. So we are in process of building 16 units. And this is the first one. And but we said that maybe it could be great to open the discussion to anybody who is interested in this project. So we opened the box and then we are now, I think we're 50% online, which is perfect. And so be all welcome. Anyway, in my mind, I will mainly talk to the participant of this first one. And well, maybe we can start with a short presentation of each of you, if you agree, of the participants. So there is almost 14 or 15 people. If you agree, maybe we can start with Olivier, because you are one of the participants in this project, of course. And then I will give the mic to other people here.
Okay.
Just the idea is, I mean, to build the community and share, know who is participating, and maybe we'll set up something like a distribution list to share our experiences with the Uvex. Okay, go ahead, Olivier.
Okay, so my name is Olivier Garde, and I have the opportunity to buy the first series of the Uvex. So I am here because I love spectroscopy and I have many good things about the Uvex. So I think I'm going to learn a lot with this new spectrograph.
Wonderful. I see. Well, maybe Ken Hudson, you can say something quickly.
Sure. I'm Ken Hudson. I'm located in New Mexico in the United States. And my spectroscopy experience has been primarily with the LIRES, but a little bit with ALPI. And I'm very excited about the Uvex, and Francois knows that. I've been talking to him ever since the Uvex first came out. And so I'm looking forward to participating in the project and working with the Uvex and seeing some spectra in the UV and the near IR. I think that's going to be really fun.
Thank you, Ken. Thank you, Ken. And well, by the way, your English is perfect. This is a way to say that mine is not perfect, but I do my best. And
I do my best, Francois. Thank you.
Okay, maybe Sean Curry, can you say some words?
Yes, Francois. My name's Sean Curry. I'm located in Southern Oregon in the United States. And I've been a pretty heavy ALPI user, but only for the last year or so, but submitting data to the various databases and really enjoying it. The ALPI is currently on my Takahashi FSQ106, but I have a brand new PlaneWave L350 mount up and running. I put my CDK 12.5 on that and plan to put the Uvex on that and run the ALPI simultaneously on the existing system so I can compare the two. And just looking forward to a broader spectral range and a little higher resolution. And I love working with new hardware, so really looking forward to it.
Thank you, Sean. Wonderful. I see that Gary Walker. Gary, you are online also. Can you say a few words?
Yes, I'm Gary Walker, and I've taken exactly 0 spectra. I'm the newbie here. I've used an SA200 a little bit, and I'm primarily putting together a system to try and crack the nut on robotic spectra, part of a bright star monitor for AAVSO, but in spectra. And I just today got my CDK 14 and L350 mount, and it's sitting down in the garage. And we had 4 inches of snow last night, so I'm trying to unpack it and attend webinars and so forth. So it's probably going to be cloudy for about a week.
Wow. Well, by the way, I do have some snow here also, and I've not been able to observe that much these last days. Thank you, Gary. Maybe I've seen Jacques Michelet. I've seen that you're online.
Yeah, I'm Jacques Michelet. Can you hear me?
Yes, we can hear you and we can see you, Jacques.
Okay, that's fine. Jacques Michelet, located in the Grenoble area, not that far from Shelyak facility. I'm the happy owner of the LISA spectrograph and a few experience. I'm still a beginner on spectroscopy, but I'm trying to learn hard. And as usual, when you have a new spectrograph, the weather is bad for a couple of days. So
oh, yes.
We'll have to wait for some better days. That's all for me.
Thank you, Jacques. Thank you. I think that's Peter Velez is online also. Maybe, yes.
Morning, everyone. Yep.
Wow.
I'm coming to you from Sydney, Australia, so it's very early in the morning here. I'm operating with ELISA as well on a CDK 12.5. I've been doing spectroscopy for a while, but really getting into it in the last year or so. My rig is up at a remote location up near Siding Springs Observatory. So one of the really attractive things for the Uvex for me is the ability to operate it remotely, to adjust it with the external units that I think you guys are working on.
Yeah, perfect. And by the way, this is great to see your face because we have exchanged a lot of emails, but I think this is the first time that I see your face. So great. Thank you for being here.
Good.
Early in the morning. Wonderful. Thank you, Peter. Now maybe Michel Verlinden. I see you are here also. Can you say a few words?
Bonjour. Je préfère en français, mais si tu peux traduire juste après.
Yes, okay. Do it in French. Okay.
Alors, je fais de la spectroscopie depuis 2015. J'étais au workshop de l'EHP et j'ai appris à utiliser plusieurs spectros, le LIRES, l'ALPI, et maintenant l'UVEX expérimental, que j'ai juste réussi à régler. Et j'attends beaucoup de l'UVEX de Shelyak, qui sera, je pense, plus facile à régler.
Okay, so in few words, what Michel said is, well, he started the spectroscopy in 2015, and he came at the OHP, and he already has several instruments, and he already has a UVEX in 3D printing, and he's impatient to see the UVEX by Shelyak which has exactly the same optics, but which is more, I mean, industrial. Okay, I hope I didn't forget to meet. Moi, j'espère que j'ai dit à peu près tout ce que tu as dit. Enfin,
Oui, en effet.
Thank you, Michel. Thank you, Michel. Maybe, I don't know, Stéphane Charbonnel, are you on board? I'm not sure. Olivier, you know if...
Sorry, my...
Yeah,
my,
okay.
Yes.
Wonderful. So I can see you, Stéphane.
So in French or with keywords in English?
Like you want, like you want.
Ok, donc je suis Stéphane Charbonnel et je fais de la spectro depuis quelques années, un peu plus d'une dizaine d'années. J'ai eu l'occasion de tester l'ISHEL, l'ISA et le LIRES aussi. Et l'avantage de l'UVEX, c'est que je le prends plus pour un instrument où je vais pouvoir essayer de découvrir ce qu'il y a dedans, plus que le l'IRES ou le LISA ou l'ISHEL que je n'ouvrais pas du tout. Donc, je pense que l'UVEX sera plus adapté pour, entre guillemets, jouer avec, plus que l'ISHEL et les autres spectros que j'ai utilisés.
Okay, so what Stefan said is he started in spectroscopy for more than 10 years now. He has an ISHEL, he has a LISA and a LIRES also. So he's one of the really experienced guy in spectroscopy. And you said that you're interested with the UVEX to play with the instrument itself more than with the other spectroscope that you have. That you didn't want to open them, and you say that with the UVEX you can play with it and maybe open it. I think this is, Stefan, this is a very, very bad idea, in fact, because the UVEX is really the first instrument that we don't need to open. So you can really tune it and play with it without needing to open it. So of course you are allowed to open it, but you don't need it. So anyway, we'll see that later on. Oh, I see Christine. I've seen your name. Yeah, yes, you said hello at the beginning. Christine, are you around?
Yes, I'm okay.
Perfect.
I know. Ah, you said Christian.
No, Christine. No, go ahead.
Yes, I'm almost a beginner at recording spectra, but as I was a teacher, I like looking for what's wrong in the well-known software Demetra.
Oh.
Hello?
Hello, yeah, the communication was not good.
Yes, no, it wasn't good.
Okay, so Christine, anyway, you each time that you discuss, you say that you are a beginner, but I think that now you are a beginner for 5 or 10 years now.
5 only. 5 only.
5 only. Okay. Anyway, thank you, Christine. Is Jim Grubb around? I'm not sure to have seen your name. Maybe Olivier, you can tell me if you see him in the list.
No, I don't think he is here. No.
Okay, and also is Christian Buil
yes,
around?
Christian is here.
Christian, if you want to say a few words.
Hello.
Hello. And if you prefer in French. Hello, Christian.
Hello. I am the prime conceptor of Uvex, but it is prudent to speak in French. Sorry.
You can do it.
Non, c'est très simple en fait. Je suis très content de voir cette communauté, évidemment. C'est toujours très, très valorisant et très gratifiant de voir effectivement les gens utiliser ce qu'on a conçu. Je pense que c'est un spectro qui a beaucoup de capacités. Il y a beaucoup de découvertes à faire. Il y a une vraie rupture. Et c'est formidable qu'après avoir fait des prototypes en 3D, aujourd'hui, ils naissent sous la forme que vous allez voir maintenant, qui est celle que fait Shelyak et qui est un produit, je crois, vraiment superbe.
Okay, so in few words, what Christian says is he says that, well, he's the initiator of this instrument, of course. He's the initial designer of the Uvex, and he's very happy to see that a community is growing around this instrument. And he says it's very interesting experience to see that after having made a lot of prototypes and different version of the Uvex in the 3D printing, then it's great to see an instrument well made by Shelyak in these conditions with this the quality of the instrument. So that's great. And well, thank you, Christian, and of course thank you for your major contribution to this project. Okay, maybe is Wayne Rosing around? I'm not sure. I didn't see you. Wayne, can you tell me if you are here?
I don't see Wayne here. No, I don't see it.
Okay. And the last, if I'm right, Vincent Boutard, are you around?
Hello.
No. Yes, Vincent. Hello.
Do you hear me?
Yes, I can. Yes, and I can see Albert. I can see Albert behind you.
My best friend.
Good. Anyway, a few words.
I'm Vincent Boutard from Colmar in France. I'm working in the Optic Unterlinden, famous dealer of telescopes in France. And I will use the Shelyak Uvex for demonstrate. I don't know if it's the real world, but
demonstrator. Yeah.
Yes, as a demonstrator for the company. So I hope all will be fine.
And you will use it, if I'm right, remotely.
Yes.
So
yes.
Your observatory
from the
is
south of France.
Yeah. Wonderful. Well, thank you very much. Thank you very much to all of you. Thank you for participating in this project. This is important to have guys like you to help us to start the project. And now I really count on all of you to give us, well, to make as many observations as possible and to give us as many feedback and to help us to improve the product, to make it alive, working, and so on. So that's great. Well, maybe I can share my screen and we'll start. Olivier, I cannot share my screen. If you can allow me to share my screen, sorry.
Okay, you can share the screen. Okay.
Thank you. Can you see it?
Yes.
Wonderful. So as I said, this talk is really about this first trend, the first series, and I want to give you a quick status of the project and of the planning and so on. So what is the current status? And it's moving very fast. So I've included here some things that we did today. So it's really last minute informations, and all is going fine, all is going well, and it's really a pleasure to work on this project. Then we'll have a quick hardware presentation of the instrument. And I will show you the Uvex. I will put it in hand, and we'll also have a software status or software demonstration where we are with Demetra Uvex. So we still have to work, but we have some very good elements to show you. I will quickly talk about the motorization module at the end. I know that a lot of you are expecting this motorization to be able to remotely control the instrument. And of course, we'll have questions and discussion at the end. As long as you want. Well, by the way, I think that the meeting should last for 1.5 hours, maybe up to 2 hours, if this is okay for you. And but anyway, we are not very numerous. So if you want to interrupt me at any moment to ask questions, please do it. Open your microphone and do it. And if you prefer, write something in the chat. And Olivier will interrupt me if this is required to answer your questions. Okay. So, you know, this is very important that a spectroscope is not a black box. You said, Stefan, that it's you want to open the box. So we don't want to make a black box, but we will ship it in a black box. And this is something we are very proud. And I think we can all thank Olivier for this, because he did ask for a long time to put the Uvex in a great case. So this is what we are doing. But again, this is important not to have something when we are doing spectroscopy and when you are doing science. It's important that you can really understand and you can access what is inside. So it's important that we open the box and we see what is inside. And well, I was kidding, Stefan, when you said that you want to open it and to see how it works. Of course, you can do it, but again, we don't need it because everything can be, every important tuning can be done from the outside of the instrument. Okay. Well, and a few words, so something which is important to me. Today we are talking about techniques. We are talking about the instruments and the software and so on. But this is I like to say each time that the most important is that we use this instrument to do science on the sky. So I'm sorry, we'll be very technical tonight, but or today for the Australian guys. But it's important that that we do technique really for doing science. It's not just doing technique for technique. Okay, so here is the status of the project. Now we have received all the parts for the first run. Okay, so as usual, we have 60–70% of the parts that arrived some time ago, and of course we did wait for the last weeks for the last elements. The last elements that we get a few days ago are the springs. We made some springs on our own specifications to attach the mirrors to the mirror holders. So so we have received them, and they're working fine, and that's great. Well, by the way, I didn't say that online we have also tonight Philippe Egea, who is the mechanical engineer in charge of the design of the Uvex within Shelyak. So he is online. Hello, Philippe. And we also have Nicolas Durand, who is the designer and the developer of the Demetra software. Okay, and maybe Amin also is here from Shelyak. I've not seen his name, but he's in charge of logistics, and he wanted to participate. Sorry, I come back to the presentation. Well, we have built the first units. In fact, we have built 2 units at the moment. So on my desk tonight I have the initial prototype and the two first units of the first series. And normally, well, tomorrow or Friday, maybe we'll have the 3 next ones. And the idea is that next week we will work with our usual partner, which is a subcontractor, well, already a partner for a long time. They are close to Shelyak, and we will work with them all next week to train them on the assembling on the instrument and on the tuning and the testing and so on. And so normally we should be able to ship the first unit to the week of the 8th of February. Okay, so it is not next week, it is the week after. Again, if we don't face any major problem during these phases, but now I'm quite optimistic. We have seen some small problems last days, but we have been able to find solutions very quickly. So it's very exciting because this project is coming real, and we well, it's a pleasure to see how it works. So we have the manufacturing procedure, which is almost done, which works well, and we are still working on the tuning procedure. I will show you a few images, and by the way, we decided that. To do the tuning of the instruments during the manufacturing process, we'll use an optical fiber, a very small optical fiber, which is perfect to tune the most important parameter in this instrument, which is that all the optics is perfectly in a plane. Okay, so if it's in a plane, we have the very best quality of the instrument. Okay, and well, something interesting also is that we will use something outside of the Uvex to tune the grating modules. So we will have to precisely tune the angle of the grating versus the axis of the guiding module, grating module, and this must be very precise. And then we have made a small tuning bench. I don't know the name exactly, but a small tooling to be able to tune that outside of the Uvex. Well, that's it, I think. Now maybe we can switch to the demonstration of the Uvex itself. I will stop I will show you very quickly how to connect the telescope to the Uvex to the telescope through the LP guiding module. And get access to the slits. We'll look at the camera attachment and the tuning, the rotation of the tuning, and we'll look at the how to change the grating, which is very, very simple. The tuning of the cylindrical lens, and the well, this is really something that you should not have to do on your side, because we'll do it during the manufacturing process, but we never know. And this tuning, which is quite sensitive, is also accessible from the outside of the instrument, which is the latest change we did in the design, and I think it was a good idea. In fact, I will show you. Okay, so I will switch. I will stop sharing my screen here. And if it works, fine. So can you see my desk?
Yes, it's okay, François.
Okay, so let's start with the black box. Okay, so this is the case, and well, I have the camera just beside me, and so this is the box, and we have a very high quality case, and in which really we can put the Uvex in total security. Okay, so and we have some room to put some. Oh, sorry, I don't have it here. Oh, I have one here. Sorry, one second. And inside, sorry, here am I. We have some the grating modules put in this box, so I can put the grating module up to 3 grating modules in the box, and if I open it, so it is in a case. So this is in this one.
François, please, can you put your microphone on your head, because we don't understand.
It's only a question of microphone. It's not a problem of English.
That's better now.
Okay, thank you. So this is the grating. On this one, we don't have the grating, but this is the grating holder, and then we can put it in the box and put it in the case. Okay, so now let's look at the instrument more precisely. So this is the second unit, and can you see it? Yeah, I think that's so fine. So first you can well, in this case we have an ZWO camera. This is an ASI 183, if I'm right, And so this is the camera that we recommend, the main recommendation we have for this instrument so far. And you can see that very quickly you attach the camera, you attach the telescope on this side, and and you can of course just you can loosen this screw and move the leader here, the index, to look at which part of the spectrum that you are interested in. And when you have chosen the position, you just have to tighten the button here, and then it becomes very strong, and there is no risk that the angle is changed. Okay. By the way, we have put, if I show you that, we have put the zero order in this position, and we also have a small hole in this part that maintains the Vernier. I think we can say the Vernier in English. So this part, and of course we have different Vernier for the different gratings, and this is something which is very impressive at the beginning when you start playing with the instrument. So this is the Vernier for the 600 grating, which is the nominal grating of the instrument, and we have different Vernier for the different gratings. And if you look at the smallest, the 150 groove per millimeter, the angle to cover the whole spectrum, visible spectrum, is very small, and it is very, very sensitive. And of course, if you put the index anywhere else, you will not see anything, and you will not have any spectrum. And so it's very different, of course, with the 1800 groove per millimeter grating, which is the most important, because in this case the scale of the spectrum is huge, and then we will use in this case the full capacity of the scale. Okay. So the next one, to do the focus of the instrument once it is on the telescope, you just have to rotate this small button, and you have a counter on it, so you can really record the exact position where you want to put the M2 mirror position, so to do the focus of the instrument. And so this is very precise, and you have really a very great precision, and it is quite smooth to move, so it's really easy to move and to tune very precisely. And,
François, I have just a question from Jim. Is there any adapter needed to connect the 183 zwos camera to the Uvex?
Well, so I come back to this camera, the camera attachment. It is, you have a small ring here, which is provided with the Uvex, and the standard one is made for the ZWO cameras. Okay, so you remember that we have a strong constraints on the camera, so we must have a very short back focus camera. Okay, so we cannot put any camera on the Uvex, because the image plane of the spectroscope is very close to the mount of the camera. So we can only afford to have short back focus cameras. And we can adapt different cameras. We can adapt the QHY, the ZWO, and the ATIC cameras. And for each of them, each brand, we have different adapters, mechanical adapters. So the one which is shipped in standard with the Uvex is the adapter for the ZWO camera. Okay.
And that allows the back focus to be correct right out of the box. Then it sounds like.
Yes, absolutely, absolutely. Well, by the way, hello, Jim. And the camera is fixed. The position of the camera is really given by this adapter, and this is why we have different adapters. Also because we have different ways to attach the cameras. But really the position is fixed, and then the camera is strongly attached. So I can really take the instruments by the camera. There is absolutely no movement. Okay, and the focusing is made by moving the mirror here that will focus the image on the sensor. Okay, and there is also the question of tuning the rotation of the camera, okay, in such a way that you have the spectrum perfectly horizontal in the image. And to do that, we have 3 screws. So maybe I hope that you can see it on the image. We have one which is here, one which is here, so I can untighten it, and one which is on the other side. In fact, so we have 3 screws, and this one, this one, this one. You can just loosen them a little bit, and then you can rotate the camera as you want, and tighten again, and that's it. Okay, so it's really something easy to do on the table or on the telescope also. I recommend to do that, of course, on the table before putting it on the telescope. Okay, so this is for the camera attachment. And this is the other point is so the entrance of the instrument is here. Okay, so I've removed the small protection, small cap, and you can see the slit here. Okay, and you can see that we have 4 screws here. So I've removed 3 of them, and if I remove the last one here, I hope that you can see it. Then I remove that and I can access to this part, okay? And this part is the part that you will attach to the LP guiding module, okay? So this is the way, the idea is that you remove this part, you attach it to the guiding module, LP guiding module, and then after that, you will reattach this part on the Uvex, and then by doing this, you do the attachment with the telescope. By the way, if you are not using the LP guiding module, if you want to use another system, we have a 2-inch thread. No, not 2-inch. Sorry, a T-mount thread around here. I hope that you can see it. And well, anyway, you can also use these screws to attach it somewhere. And by the way, using this system of the 4 screws on the side to attach the part is a very simple way also to if you need to open the system, for instance, if you want to clean up the slit or something like that, you can easily access the slit by removing these 4 screws from the instrument, and then you remove the Uvex from the telescope. Okay, so this is the way to attach it. What else? Well, changing the grating. So I explained you how to change the grating angle, of course, but there is also the system which is very simple. You just have to open the box here. We have a small spring. And by the way, maybe you can see it. At the end, we have made a small 3D printed part. This is really a last-minute solution to make sure that there is no effect of the spring on the rotation of the grating, and well, I think it works fine. And so we have a small spring in this cap. I hope that you can see it, I'm not sure. And it pushes on the grating, and then you can just attach it, and here is the grating. Okay, so this is the grating holder with the grating, and there is a small arrow to show you how to put the grating if you don't know how to put it. And you can see that on the holder, you also have some shape here, a cut here, to show the direction of the grating. This way, you know that when you put it in the box, it must be something like this. And at the end, you have something like a Pokayoke system that makes that you cannot put it in the wrong direction. And when you put it back in the system, it will come exactly at the same position. Okay, so you can rotate it, but at the end, when it is in its place, it will recover exactly the angle that you had before removing it. And we did some experiments. If you remove it and put it again, really you can the position of the spectrum will be exactly the same, because on the other side, the index position didn't change. Okay, so by the way, if you change the grating, or even if you remove the grating and put it again, in any case, you will have to redo your calibration images to make sure that you have a good calibration. But really the position of the spectrum is very stable.
We have a question from Vincent. want to know how could we adjust the angle between the camera sensor and the grating inside Uvex?
The camera sensor and the grating inside the Uvex. I'm not sure to understand what it means. So the grating, the angle, you cannot. Something. Well, I don't know if this is your question, Vincent, but there is something important. You know that. So a spectrum is a multiple image of the slit. Okay, and then of course, if your slit, which is here, has a small angle, then all the lines of your spectrum will be slanted in your spectrum. Okay, and if you want to have the lines perfectly vertical, then you have to just loosen these screws around the slit and make sure that you can rotate a little bit. And by the way, we have put different solutions here. So we also have a solution with the oblong holes here. If you really want to have if you need to have a higher angle to tune this angle. But so far, I think it's not useful for a normal usage. Okay, is it what you wanted to know, Vincent? I'm not sure.
Ouais, François?
Yep.
Oui, je te le fais en français.
Yes.
En fait, c'est simplement pour cadrer en fait comment dire, le capteur, pour être sûr qu'on soit bien toujours dans le même angle. Parce que on peut régler la rotation de la caméra en fait.
La rotation de la caméra, oui, comme ça. Yes.
Ok. Et donc ça c'est réglable et tu peux serrer.
C'est ce que je disais, tu le serres ici, en fait, tu as 3 vis à peu près 120 degrés.
Ah, ok.
Et tu peux accéder et tu desserres comme ça.
Okay,
so the question was regarding the rotation of the camera. So this is what I explained. You have the Swiss screws. You can loosen them and then rotate the camera. Okay, so well, I don't do it now because I don't want to spend too much time, but this is very easy to do. Okay, well, now the angle here is fixed, so you cannot change, you cannot rotate the camera in this direction, of course, but around this axis, its axis, you can do it. Okay, after that, so these are the major tuning points of the system. Now we have 2 other tunings which are quite important. The first one is the cylindrical lens. I guess that you remember or you have seen that at the end of the optical path, optical schematic, we have a cylindrical lens to make the spectrum very thin. Okay, so if we don't have this cylindrical lens, because of the astigmatism of this optical combination, the Vernier-Turner architecture, we would have a very wide spectrum. Okay, and well, I switch. If I show you with my hand, you have to see me. So we will have a very wide spectrum, and then at the end we have put a cylindrical lens to make it very thin. And this lens must be tuned to have the right position compared to the camera sensor. And to do it, we have this system. So I share again the video. Okay, so you have a small screw here, so you can just loosen this screw, okay, and then you can tune the position of the cylindrical lens. I hope you can see it, okay. And here we have a small screw that is a stop. Then you can tune precisely the position of the cylindrical lens. Okay, I will show you just after what is the effect on the image and how you can decide if it is properly tuned or not. Okay, so and then you have a system that memorize the position of the system. Okay. Now there is another tuning, which is really the one that I told you that it is not, normally you shouldn't have to do it, but this is the angle of the M1 mirror. And this is something really new that we have designed recently, and we are just discovering now, and it works fine. This system is that you can see here that I have two holes, two screws, one here and one here. Okay. And well, this one is behind the vernier. This is why I removed the vernier. And if you tighten one screw and loosen the other, well, if you loosen one screw and tighten the other one, you will act on the grating, on the first mirror angle, which is critical for the quality of the spectrum at the end. And now I will show you exactly what is the effect of these different tunings. Okay, so I think that's it for the showing the instrument. Again, I'm sorry, Stefan, we don't have to open the box. So this is not to make it a secret. You can open it.
Okay.
Well, I switch to the camera. For me, this is very important. I know that a lot of people is afraid to open the instrument. I can understand it. And I'll always invite you to open the box and know how it works inside. I think it's important to know what you are doing, but I perfectly know that a lot of people are afraid to open the instrument. So in this case, this is not required.
We have a question from Gary. Gary, he say, I would assume that the adjustment of the angle is best done on the bench, not on the telescope.
This is a very good question. Yes, this is very important. You always have to tune the instruments on the table when we're in good conditions and well positioned, the instrument is stable and so on. And really, absolutely, you're right. You better have to do it on the table. And by the way, I always recommend to the beginners to do the first spectra on the table. You can use the light you have, the office light, the sunlight, or the sky light. You can take any kind of light source to do spectra and see how to make all the images you need, to see how to process your data and so on. And then once you master your instrument, your spectroscope, you can put it on the telescope. And this is really the way to do it. Anyway, in this case, in the case of the Uvex, if you have to do some fine tuning, you can, because all is accessible from the outside, you can also do it when the system is installed on the telescope.
And we have another question from John about the camera. He say, why do you recommend a Cmos camera?
Well, I think that we could have a workshop, a dedicated workshop on these questions. This is something not easy. Well, our official recommendation today is to put in ZWO ASI 183. It looks to be the best candidate today, but we know that we have some new cameras that are arriving, and the Cmos cameras are moving very fast. And so this is the recommendation today, for sure. But maybe in 6 months from now, it would not be the case anymore. Okay, so I know that in fact, we are expecting some new cameras that should be much better on the paper. So this is really the next generation of the Cmos cameras, and it's very interesting. There will be probably more expensive than the 183, but well, this is a complex question, really. And so you can use an Attic 460, for instance. It will work. What I can tell you is that the Uvex can cover a sensor up to 20 millimeters, or maybe 19.35 or almost 20 millimeters. So above, there is no interest because you will have some vignetting inside the instrument. So it's really a maximum usable length, which is 20 millimeter, and that's it. Okay. I see the question from David. How sensitive is the adjustment of the Uvex to the temperature? So well, I've not been able to do my own data on this because I've not been able to do this this measurement myself. So I'm not very comfortable. I know that all the tests that we made at the OHP, we have put the instrument inside a fridge to see how it behaves, and the result is very good. In fact, so it looks to be very stable. Okay, and so I'm quite optimistic, but I don't have real data and strong data to show you, and I hope to do it very soon. And that's it. And by the way, if you have some temperature sensitivity, which I don't think so, but we'll have the capability soon to remotely control the focus. Okay, I see another question. Any drawback using a CCD camera instead of the Cmos one? Well, no, you know that the cameras. This is the kind of question, because for this question we could spend a full workshop on this question. The cameras are moving from CCD to Cmos. And we are really at now at the moment where the Cmos becomes more get more performance. So far for a few years now, the Cmos have a better price quality ratio. But so far the CCD was still better at the end. But with the latest generations of Cmos camera that are arriving, well, including this one, the 183, really the quality of the absolute quality of the camera is really comparable to the CCD, and it is cheaper. Okay. Any idea of the mass of the Uvex? Well, that's not heavy. I think we did measure it.
Yes, it's 1.2 kilogram, I think.
Okay, without the camera.
Without the camera, yes.
Well, 1.1 or 1.2. It's not that heavy. If you are familiar with the LARES3 or with the LISA, the Uvex is smaller. Okay, it should be almost the same weight, but it is smaller. Okay, so I come back to my presentation. Can you see it?
Yes, of course.
Okay, so I think I've covered almost everything here. Now, just to give you some illustrations, I've made some tests a few days ago with a photo lens in front of the Uvex, and the advantage of the photo lens is that you can change the f ratio, the aperture of the lens. And this is something which is very important with the Uvex. You know that we say the recommendation is to use an f8 telescope, and you can go up to f5 aperture, f5 ratio. Well, if you are at f5, you will not lose any light. So you will not have any light lost by vigneting. But you have to know that the faster is the beam. So if you open your beam, so in this case it was a f2 photo lens, and in this case you can see that the quality of the spectrum is quite good in the middle of the spectrum, but it is really degraded. The quality decreases on the edges of the spectrum. Okay, on the top and on the bottom. So if you have something, an optic very close, like f10, or in this case f22, really all the lines are sharp from the top to the bottom. It's wonderful. We think that really the f8 is the good compromise, because you can see that the quality is lower at the ends, but it is still usable. So you can work with it, knowing that in any case you have really to use the small center of this part. This is something important here. Uvex is not really made, adapted for extended objects. Okay, so if you are observing a star, you have just to put the star in the middle, and then the spectrum will be in the middle of the image here. In this case, the quality is the best. If you have an extended object, the quality at the edges will not be the same. So this is really something important, and we can see it perfectly here. So the quality is, in this case, the resolution is much lower at the ends. Okay, so if you use it at f5, it will work. You will not lose any light, any photon, but the quality will be a little bit lower. Okay. Then the tuning of the cylindrical lens. So I explained you that you can tune the cylindrical lens to make the spectrum, the spectrum thinner, as thin as possible. In fact, the best way is to use the solar spectrum. So by the way, this is the solar spectrum, and this is the beginning of the UV. So somewhere it should be the end of the visible range here, I think. And this is the UV here. You can see the small lines that are wonderful here. And the way to tune the cylindrical lens is that when it is properly tuned, you can see that the edge of the spectrum on the top and the bottom are sharp. Okay, if you change the position of the cylindrical lens, you will see that the edges will become fuzzy here. Okay, so this is really the way. The idea is to have something sharp here, which is the reflect of the fact that the spectrum itself is very thin. Okay, and this is something easy to tune. I really recommend to do that on the sky spectrum, and again on the table when you are in very good conditions. Okay. The next is this question of the tuning of the M1 mirror. So I've put some parentheses to say, well, you shouldn't have to do it, but I cannot resist to showing that. This is the instrument which is, well, this is really the instrument we have here, which is properly tuned. And when it is properly tuned, you can see that the spectrum itself is right in the middle of the image vertically. Okay, so it's really in the middle, and you can see that the highest quality of the spectrum is in the middle of this spectrum. Okay, so the resolution is lower here and here, in the top and the bottom, but in the middle the quality is the best. Okay, now I showed you how to tune. We have two screws, one here and one here in the middle of the vernier. So you can see the parts that attach the vernier below. And you have the two screws. And you can see that we have a round shape here. And then if I loosen a screw here and I tighten here, I will rotate, I will change the angle of this, what we call the M1 mirror. Okay, and we know that this is critical, this is key for the quality of the result, that all the optical path is in a plane, and by doing this you can tune this. Okay, and then we have made some changes. We have changed this tuning. It was this morning or yesterday, I think, with Philippe, we did that. And this is just to show when I loosen on one side and tighten on the other, the result is that the whole spectrum will move vertically, okay, toward the top or toward the bottom. But the most important is that in this case, you can see that the best quality is somewhere here, and then the quality decreases here in the top. And this is the reverse here. So the best quality is here, and the quality decreases in the bottom. Okay, so this is like if, in fact, the optimal quality is always here in the center in the image, and then by moving the M1 mirror, you can select exactly where you will put the spectrum, and at the end you can have something very symmetrical. Okay. And I told you that on our side we will do the tuning with a fiber. In fact, the setup we'll use is this one. You can see in the picture here. We'll use a very small fiber, which is, I think, 4 microns diameter. So this is absolutely not the same fiber, multi-mode fibers that we use for DHL, for instance. This is a very small fiber, and you see the result here. And if you do a zoom, if you zoom on this emission line, for instance, you will see something like that. And when the system is properly tuned, first, the spectrum is in the middle of the image vertically. And to have a very, fine tuning, we have a very symmetrical pattern of the lines. Okay, so in this case, it's not perfectly focused, but it is better to do it in not exactly focused situation. And if you change the M1 position very slightly, you have something like this. Okay, so the tuning criteria is really to have a very good symmetry of the shape here. By the way, something which is, well, this is not linked to Uvex, but I think it's very interesting. You can see here that we have 2 bands in the image. And we said, hey, what that? Where does it come from? And in fact, we did understand that we are in the infrared part of the spectrum, and we are using a small fiber, but you know that the fiber is very small, but you have a core. So this is the core, which is small, but you have this part. In fact, the fiber optics is a mix of two different glasses. And in fact, what you can see here is the external position. This is the infrared light that goes through the shield of not the shield of I think the gain, the outer part of the fiber. Okay, so this is kind of pollution, and this is why we prefer to have fibers with the shielding, with a stainless steel metal shield to protect again light leakage. It's interesting to see it here. Okay, so and we are sure of that because you just have to put anything on the fiber in the same system, and immediately these bands disappear. Well, okay, so it was just for kidding, but this is interesting. Let me check. Yeah. Well, now let's switch to I think I've finished with the hardware. If you are okay. I don't know where we are in time. Well, we should be okay. I think it will be great. Now we can switch to the small observations that we have done. So I don't remember who said that there were some 4-inch snows fall a few days ago, but this is the same here. So I'm close to Grenoble. I am in the mountains. I'm at 900-meter height, and we have some snow at the moment. And really, during the last weeks and even months, it was very, very difficult to observe. So I would have loved to do more observation, but I was not able to do it. Anyway, a few days ago, we had one clear night, and I was able to do a short observing session. So it was very quick, but anyway, I think it was interesting anyway. So I used the prototype, so not the first run unit, but the prototype. And it was with the 600 line per millimeter grating, which is the standard for the Uvex. And I choose to go to the blue end of the spectrum and to focus on the blue part of the spectrum. And I use my setup. So this is my setup, really in the garden at 10 meters from where I'm talking right now. And I have an RC8 telescope. I have on the system, I have an Attic horizon camera, and I use the Indie server because I like to work under Linux, and then I'm using this system. Well, by the way, I can also spend some time on this. I'm using a Raspberry Pi for controlling everything in the observatory. Well, I observed just few stars. I just took some bright stars in the sky. I was not very well prepared to do that, and now I propose to show you the result of these observations. Just to figure out how it works. So when the weather is better, I can open the box remotely, and then the telescope is inside. And so it was a few days ago with the Uvex prototype installed on the telescope. So I have the RC8 telescope. I have a 10-micron mount, which is wonderful. We have made a special plate here to attach the telescope to. It is an elongated plate to adapt it, because if I didn't put that, I would have been obliged to put a big weight to balance the instrument. So I did prefer to do that, and it works very fine. And by the way, I've replaced now this quick and dirty solution for balancing the wool instrument by a cleaner solution, but I don't have the picture. And this is, well, this is where I am at home, how I can control everything from home. And this was at a day when I did do some observation on the table. And by the way, you can see here the 135 millimeter photo lens that I use to do the previous images. Okay, so now I propose to switch to the Demetra software to have a live demonstration of the Demetra Uvex version, and then we will see the images that I made a few days ago. Okay. Regarding the software, what is important is that the differences that we have compared to the other instruments. So you know that in Demetra, we have one version of Demetra for each instrument, and we really want that Demetra is focused on one instrument. So it's not a universal software to manage any kind of spectroscope, like ISIS is, for instance. But this is a dedicated instrument, so this is another approach. And then we wanted to have a Uvex version of Demetra. The main differences are that first, we have a very poor flat signal in the blue end. You know that Demetra, Uvex, can go very far in the blue and very far in the red, and this is one of the most important advantage of this instrument. And the problem is that in the flat lamp, we have almost no signal in the blue end. So to avoid any, to avoid adding noise in the image in these parts, so we have chosen to replace the flat image in the blue end by a constant value. Okay, so and if you have very high temperature lamps which are not too expensive, please tell us, because it's very critical. Anyway, I think it works fine. So this is something that Christian Brill did define and it did in ISIS software. So we did reuse this solution in Demetra. The second major difference with the other instrument is the calibration algorithm. So you know that for the LP, for instance, or for the LISA, well, also for the DHL, but it is quite different in this case, we have an automatic algorithm to do automatic calibration. And this algorithm have one condition to work properly, which is to know, to be able to detect a series of reference lines. The problem with the Uvex is that we can rotate the grating, and then we don't cover all the visible range, well, depending on the grating you are using, of course. And then from one configuration to the other, you will not cover the same wavelength domain. And then we had to adapt the algorithm to make possible to detect the angle position. So I will show you how we have defined this solution. And the other point is that well, because we recommend to have Cmos cameras, the processing is almost the same with Cmos and with CCD, but there are slight differences. One of them is that in the Cmos cameras, we have what we call the telegraphic noise, which are random white points in the image. And like hot pixels, but a hot pixel is always at the same position. And this is not the case for the telegraphic noise. And the telegraphic noise is linked to the reading of a pixel, not to a defective pixel by itself. So this is during the reading operation that it can happen. And this is something, I think it is linked to some quantum mechanics, and well, I don't know the details, but we can see it very easily on the images. And this requires a specific processing to avoid having bad values in your spectrum. At the moment, so Christian did propose a solution that is applied in ISIS today, which uses the fact that most of time in the Cmos cameras, we have small pixels. So it means that we can use the small pixels, and then we can do some filtering inside the image to avoid this telegraphic noise. The problem is that it requires, in fact, we lose a high quantity of information of the image, and this is really dedicated to a small pixels camera. And the feeling we have is that we, in quite very soon, we'll have a Cmos camera with the bigger pixels. So we are working on another solution to avoid using this filtering and losing so much information in the image. Well, so far it works on the paper. It doesn't work yet precisely, and the problem is that we have a solution. It looks that we have a solution, but it is very time consuming. So we don't know exactly what we'll do at the end. So this is something that we still have to work on. Okay, another important point, the Cmos cameras make huge images because they have small pixels and they have big sensors. So the result is that we really need to crop the images to save space, readout time and space on the disks. And then we have improved all the cropping features in Demetra to make it really usable. Okay, so I will stop sharing my screen here, and I will switch to the demonstration of where we are today. So I switch again to, if I find Demetra, where is Demetra? Hey, cannot find it. Sorry. Where is Demetra? Yeah. Strange. Here it is. Sorry. Olivier, can you tell me if you see my screen?
Yes.
Okay, so these are the different observations that we did. So there are a few stars, Gamma Cas, the B star, the most famous B stars, and I did start with the sky while it was quite late, and so I can show you the raw spectrum of the sky. This is something interesting. I consider that this was a quick and dirty observation, so I was not very well prepared. You can see that the spectrum is not exactly horizontal. It should be better. And you can see also perfectly here that the quality of the spectrum is much better in the top part of the band here than in the bottom. So it means that the instrument was not properly tuned at this moment. Well, the point is that we did open it and we changed a lot of things. And when I did use it, I didn't want want to spend too much time to lose the potential observing time. So I did decide to use with these conditions, and to make sure that I don't lose too much quality, I just put the spectrum position here. So it's not exactly in the middle of the slit. So the middle of the slit should be somewhere here, but I did choose a quite good position. Okay, so and if I go to the to this step, I can run. Well, let's start with the gamma cast, for instance. Okay, so if I look at the images, well, by the way, on the sky you can see the HNK lines. Okay, and then I can see that I still have some information here, much lower than the HNK lines. Okay. I guess that you are familiar with Demetra. I will not spend too much time. I think that most of you are already familiar with Demetra. And in few, very quickly, you have different tabs here. So the first is for the definition of an observation. In Demetra, we are talking about observation, and an observation is a full set of data that is consistent. Okay, so we have a definition, for instance, for the gamma cast observation. We have the set of images, so the bias, the darks, the flats, the calibration images. For each image, I can double click here and I see the result in the bottom part. Here I can tune the different level of parameter. I can fit the image. I can move the image in the screen. I can show in live the profile of this thing. Well, it's not very easy to read here, but you can see the profiles in the bottom part here. Well, this is the general features of Demetra, and really again, I don't want to spend too much time on Demetra, the general features of Demetra. This is not the purpose today, but this is the general idea. Okay, and then when you have collected all the object images, so in this case, so this is the spectrum of Demetra. Of gamma Cassiope, and here I can see the profile, the raw profile, the real-time profile. You can see the emission here and the emission here, which is H beta and H gamma, I think. So we are really in the blue part of the spectrum. Again, H alpha is not in the image, is on the right here. Okay, and well, the third tab is the data reduction, and now, well, thank you, Nicola, because you did a great job even today. So we finished this first run that works fully automatically, worked for the first time this afternoon. So it's very impressive. And then you can see all the operations that are made in real time here. Okay, I just click on the run process to do automatically all the data reduction. And so, well, because it is connected to Zoom, it takes more time. So normally, I would say it is twice faster than it is now, but we can see that the calculation is ongoing. Okay, and in few seconds you will have the result. Okay, one step is completed, it becomes green here, and then you can go step by step and see what happens in your data processing. Well, again, on my computer, it goes faster when I'm not connected on Zoom. Few seconds again. So the calibration is critical. We look at it, and that's it. And and you have the full spectrum, which is calibrated. We put on the graph the Balmer lines, so H beta, H gamma, and so on. H alpha again is on the right, and this is just to check quickly the calibration. Okay, and now you can go to each step. For instance, you can go to the calibration step, look at the result. I can double click on the result of the calibration on the calibration image, and I see all the reference lines that have been catched in the profile. Okay, so this is this famous automatic algorithm calculation for the calibration. And if I look at this step, which is of course critical, I can go to the calibration tool, which is slightly different from the ALPI one. And you can have here, you have a whole tool that detects automatically. And the way to help Demetra to find, to start with the calibration is to tell Demetra a value in this area of the spectrum. This is an indication that we give to Demetra to say, hey guys, you are in this region of the spectrum. So from this, you can start working, okay? And if I want to know where I am, so I just have to show this reference document, which is the document that we made recently, and which is really dedicated and based on a real spectrum, calibration spectrum from Demetra. And then you have a lot of information here. Can I zoom? I don't know. And you can see perfectly if I compare to, maybe, can you see my screen or not when I do that? Yes, I think yes. Can you see the reference document, Olivier?
Yeah, yes. So
yeah, okay.
It's good.
Okay, so you perfectly recognize the pattern here. So you can recognize this line, for instance, is this is this one. So we know that we are close to a 49 or 40, 47 or 476 or 490, something like that. And then we have put this value here, which gives the central wavelengths roughly. Again, this is in this gray area. Okay, and that's enough for Demetra. Also, we give it the width, the width of the whole spectrum, and something. In fact, this is smaller than the actual range of this spectrum, but this is just to allow Demetra to know from where to where it must detect all the lines and do a first calibration. And in fact, we have a calibration in two steps. The first pass is based on this information. Then it will be able to recognize the pattern. And from that, it will be able, in a second pass, to extend up to the ends of the spectrum. Okay, so I can see here that I have an RMS of 0.2 angstroms, which is good. And the second pass here is, well, in this case, oh, it didn't work. I don't know why. Ah, it worked. I promised it worked. But it worked because, well, we'll see. Yeah, it worked. So this is the result of the second pass. So here you can see all the detected lines. Okay, so Demetra detects all these lines. And we have here all the list of the reference lines, okay, that are written in this document. Okay, so we consider that there are reference lines. And here I can ask to show only the associated lines. So among all this list of lines, it did consider that the reference lines are at this position. And you can see very quickly that the matching is good. So these are only straight, well, bright lines that are detected. So which is a very good sign on top of the fact that you have a good RMS at the end. Okay, so this is how it will work to do the calibration with the Demetra Uvex. This is slightly more complex than with the ALPI, again, because we can rotate the grating, and then we have to give more information to Demetra to be able to detect the actual solution. But at the end, once you have done that one time, so for a given position of the grating, it will work for the rest of the time, and you just have to do that once, and that's enough. And here you can just check, this is the check of the results. We can see that all the emissions lines have been detected, and you can check with this document if the calibration is correct or not. Okay. And so because I did change some things, of course, it did stop the step became gray. There is something else that we have to look at, which is this important new parameter, the flat threshold. So if I look at the flat image here, hop, I will remove that. Okay, so this is the flat. And this is the flat, and within this flat, we have to define a position where we consider that the spectrum becomes too noisy, or the signal is too low here, you know, and in this part of the spectrum. So when we look at the star images, if I extend the graph here, and if I look at the star images, I know that there is still some information in this part of the spectrum, but the flat has no more energy. And then we just have to define where we have to stop this. And we define in this case that the good position is something like 500 pixels, so around this position. And around this position, we do replace here the actual flat by a constant, okay? And if I look at the result with that, I can, if I change the threshold, the right click of my mouse, yeah, okay. So you can see that, well, I will do this one.
Ouais, tu es dans la zone du spectre, je sais pas si ça
So
marche.
we can see here that no, well, it doesn't change. So here it is replaced by a constant value. So you can see the value here when I move the mouse. So this is a constant value which is calculated based on this area, which is the spectrum area. And then from this part, we replace the actual flat, which becomes too noisy, by a constant value. Okay. Oui.
Si tu veux me montrer plus clairement, fais le niveau de gris par rapport aux bandes noires qu'il y a en dessous. Mais au-dessus du spectre.
Comme ça.
Ouais, mais dans la zone, parce que là, il y a la constante là, encore à droite.
Comme ça?
Ouais, voilà.
Ah oui, en fait, c'est absolu. Ok, ouais, bon, ok. Okay, so well, I'm losing our time here. Well, this part is constant, and well, I can see, I cannot show it, but maybe I can show it. No, I cannot show it because we don't see the profile later on. Yeah, we can see it. We have the profile, we can see it. So the profile is decreasing here, and then here, from here, it is constant. Okay, so this is really, again, this is to take into account the fact that we cannot use the flat in this part. And I think that's it. Well, in this case, we have used the zeta array. So this observation, as we have considered, this is a reference star, and we have built the response curve based on this star. So and reuse this response curve for all the other observations. Okay, so the result is that at the end, it is a response curve or instrumental response curve corrected. Okay, well, I've run again the full process. It will take some time, and
we have a question from Tonis,
yeah.
François.
Yep.
Is it possible to exclude some badly behaving comparison line when needed?
Yes, the calibration tool, with the time we are improving the calibration tool, and you can edit the list of reference lines that you want. So it means that you can use it, in fact, for any instrument. And I will show you if I go to the well, again, I will come back to your question, Tonis, and just to show when it is finished. So this is response curve corrected and so on. I can switch to the last tab, which is to generate the PDF or PNG documents. Okay, so again, this is there is no change with the LISA or ALPI version of Demetra, but it is useful and it works fine, and you can put a grid, you can put or not decolored profile or band in the bottom part and so on. Okay. Well, if I come back to the to the calibration tool here, Tonis, you can really, so this is the list of reference lines, and this is all the lines that Demetra must find in the spectrum, in the calibration spectrum. But you can edit this line, this list, okay? And you can add some line, remove some of them, and you can even load a new file, and you can save a file of reference line and so on. So you can really work with that. And it can be very useful if you want to have a good calibration for your particular case. You can really adapt that. And I think it's good to spend some time to understand how it works and to tune the system. Again, this is an automatic algorithm, but you have the full control on what happens. And it's always important to make sure that at least the calibration went well. So please check the RMS and check when oops, sorry, I exit from Demetra. When you are here, you can really look at the calibration step, double click here and check that when you see this document, you say, okay, so the calibration went well. Okay, I know that the system has catched all the important lines and that's it. By the way, there is something very important and quite new and quite surprising for me, to be honest. This is that we still have some lines in the very, very blue part. And I think that with this system, we can calibrate using the argon and neon lamp that we have in the LP calibration module. And we don't need to refer to a hot star spectrum to have the blue part calibration. So this is something that, well, we will validate all together. But so far, it looks like here I can use this line of 355 nanometers, and there is even another line lower, but we have to better tune the parameters to be sure to catch it. Okay, so I think it is very powerful, but for sure you have to put the hands on to make sure to understand what happens with this calibration tool. And again, once you have defined your parameters, if you don't change anything in your instruments, you observe all night long with this setup. You just have to fine tune the parameters once, and that's it for all the night, or even all your observing session. Okay. Well, very quickly, well, I see that there are some questions. I will go back to the questions soon. I've almost finished. Just to, I can show you the quick results. So if I look at, again, I did select some stars almost by chance, and I was just looking for quite hot stars, even except one. And so this is the result. And this is for me very interesting because for the first time I can see these kind of things that Christian have already shown. But well, this one I did it myself, which is totally different. So we can see the end of the Balmer lines. So it's just wonderful, and for me it's very, very impressive. Okay, and we have different stars like that. So this is another one. We can see what we call the Balmer jump. So this is the H infinite. So the last Balmer line here officially. I mean, and we can see the jump here. And so gamma cas we have already seen it. And so gamma cas, of course, this is a B star. This is a famous B star. So the H beta, H alpha has a huge emission, but H beta also and H gamma also. Okay, and even H beta, H delta here. Okay, so it's well, you know that we love the B stars, and it's always very interesting. There is beta 2. I think that I did select this one because it is a very good demonstrator, I think, of the Balmer jump things. But well, I know that there is a lot of science to do here, but I cannot tell you more at the moment. Okay, so I love the shape of the lines here, and here, hop, you have a smaller, something else than hydrogen. Okay, and so this is beta Andromeda. So this is a cool star, which is totally different. In this case, the spectrum is increasing towards the red. Okay, and well, this was the sky also, and of course the sky. So this is the sun spectrum, and we have the H and K lines here. Okay, I think that's it. Nicolas, maybe did I forget something regarding Demetra?
No, I think it's okay.
It's good. Again, this is all what I'm showing to you is very, very new. So I'm very happy to be able to show you all this tonight. Of course, we are. Well, I have to repeat each time that most of the job have been done by Christian before. So, Demetra is another way to present things, but the algorithm behind come from Christian and from ISIS. So thank you, Christian. And but I think that we have a quite interesting approach, and it's important for me that we have a tool that makes a really good result at the end. And really, for us, for Nicola and I, this is very important that you use it and you help us to improve it. To well, we already did it. I know that Sean and Tony, you're online also. You help us to improve the LISA version, and we still have to do the same with the Uvex, which is a little bit different. Okay, so I think that's it.
And we have some question about using the calibration module on the guiding module from the LP on the Uvex. Did it work?
Hey, well, of course they work. Well, I stopped sharing the screen. I change my camera. If it still works, it still works. Okay. There is something I did forget to talk about. Well, this is the Uvex prototype. So I will talk about that later on. But this is just to show you how it is assembled with this. So this is the Attic or horizon camera, and this is with the LP guiding module and LP calibration module attached. And this is the setup I'm using on the telescope. And really, we have designed Uvex to reuse these modules. Okay, so maybe we'll do other modules. So we would like to have other modules for the calibration and so on, but I don't know why. And for sure, for the moment, our recommendation is to work with these modules. Okay, does it reply the question?
Yes, I think. We have another question from Michel. How much time do we need to, I forget the question. How much time do we need to do one exposure with the calibration module in the UV part of the spectrum?
I can tell you that in the image I've taken, let me check. In the images, well, I will share my screen again. So you should see my screen with Demetra. If I look at the calibration images, I took 60 seconds, 1 minute calibration images. Okay, and with that, here is the result.
Okay, and another question.
Okay.
What is the recommended guided camera for the Uvex?
Well, well, not only for the Uvex, the camera I have here, if you can see it, the camera I have here is an ASY 174. And generally speaking, we recommend this kind of camera. So either the ZWO or the QHY version, which is a cooled version, okay, but they have the same chip, the IMX 174. And this is really I think the good compromise today, because it has quite big sensor, big pixels, and it is well, this is I think really the good camera nowadays. Again, it can change in 6 months from now, but for this one, I think it is the right choice.
We have a question, but not for the UX. It's what company manufacture your observatory? Your
well,
observatory, yes, François.
The shelter, yeah, okay. Well, I guess that well, I don't know if you are kidding or not, but this is a very a small and great company called Shelyak Instruments. But the point is, so this is something that we will offer, we will put on the market as soon as we find the time to do it. So it works, it's fine, and I would love to put it on the market and make it available, but this is not the case at the moment. But thank you for the question.
So do you have any other question to François?
Yeah, you can open your microphones.
François, I have a quick one. I really like the new Demetra calibration, especially the table showing the delta lambdas and the the calibrated lambda, the official and the delta. Can we get that backported into the Alpi version at some point?
Oh, yes. Yeah, just a question of time. Yes. The answer is, in fact, so you are talking about the I'm sharing again my screen. You are talking about this graph, right?
No, the table.
No. Oh, the table. Oh, yeah. Okay. Sorry. Okay, I didn't understand. So when you are in the calibration tool, okay. So I open this, and then the idea is to have this full table on the right when I run the calibration, and I can. Yes, we have improved that. And well, Nicolas, I think is it available right now in LP, or do we have to change anything?
Yes, that.
You hear me?
Table. Yeah.
Not for the moment, but when Uvex version will be available, this will be available for Alpi and Lisa too.
Okay,
great.
Okay, because this is a quite generic tool, and in fact, well, Nicolas did work a lot on this calibration tool for the UX, and we have improved the tool. And by the way, if I look at the, I can show all the different combinations that has been tested, and I can really, so we have improved things, and I think that this is something, Sean, that you did request, you did ask.
Yes, so Tony and I will be very happy now.
Wonderful, and then
this come from your in the Lisa session, your remarks.
And we confirm it was a good question. Thank you, Sean.
Thank you.
Any other question?
Oui. Quelle est la limite inférieure du spectro?
En longueur d'onde?
En longueur d'onde, oui.
Okay, so what Marcel is asking is what is the lowest wavelength that we can reach in the blue part of the spectrum? The
UV.
Yeah, in the UV, and the well, I think that's so this is somewhere between 320 and 350 nanometers. So in what I've done here, you can see that we can go again. I will show.
Is it depending on the captor or on the structure of the instrument?
No, this is, well, this is really, in fact, going so far in the blue part of the spectrum, in the UV part even. It is really something incredible. I'm showing that, And so in this case, you know that we are here, we are at 350 nanometer, somewhere here, and we still have some information. We have done a lot. So we are using mirrors instead of lenses to avoid any chromatism. So this is what allows to go so deep in the UV. We have improved, we have a new slit, and the slits, we have a slit which is improved, the anti-reflection coating, the IR coating is improved to be transparent in the UV. We have made some, we have extended the AR coating also on the cylindrical lens to make sure that we don't lose any signal. And then really the limit is the sensor. And well, at this position, everything becomes complex, but the main limitation is the sensor. Okay. And I know Christian, maybe Christian, you can add something here because I know that you have been down to 320 nanometers with the UVEX. Again, sorry, Marcel, je t'ai coupé, pardon.
Attends, excuse-moi, François, est-ce que tu peux basculer ta caméra sur toi, parce que là on voit le spectro et ce serait quand même mieux qu'on te voit toi.
D'accord.
Non, mais c'est déjà une belle performance et ça permet de voir un certain nombre de choses. Comme je suis intéressé par la spectromoléculaire, dans les CN, donc CN, ça marche. Par contre, il y a des CN+, et des trucs comme ça qui sont en dessous et qu'on devrait pouvoir observer, mais bon, ça a été observé en détection photographique.
So what Marcel is saying is that, well, he's interested in spectroscopy and especially in the blue parts. You have elements like CN elements for which some of them are reachable with this configuration, and some of them are still far in the
outside
UV.
the area.
Christian, if you are around, maybe you can give more information here. I know that you know that perfectly.
Hello?
Oui.
Oui, enfin, tu sais que c'est surtout, je ne sais pas si tu l'as dit, mais c'est le détecteur qui fait vraiment la vraie limite parce que les transmissions optiques des éléments que l'on a mis, en particulier, il y a du quartz en fait, hein, d'accord, ils sont particulièrement bons. Les miroirs et les coatings qui sont un peu justes peut-être, mais potentiellement on peut aller beaucoup plus bas enfin, on peut aller très bas, on peut aller jusqu'à 320 nanomètres. Mais après, c'est le détecteur qui va déterminer beaucoup de choses, en fait. Hein. On a pas de détecteurs, les détecteurs amincis Cmos existent. On a des problèmes de hublot, il faut travailler là-dessus. Mais voilà, donc il faut beaucoup de détecteurs, en fait. Hein.
Et quand tu as été à 320 nanos, c'était en jouant sur les hublots?
C'était avec les caméras standards, en fait. Il se trouve que certaines caméras à ZEO, ça m'en suis aperçu, en fait, ont des hublots en silice, en fait.
D'accord.
Et j'ai mesuré la transmission de ces hublots. Elle est vraiment extraordinaire, en fait. Elle va très loin. Alors, peut-être pas 320 nanomètres, parce que je n'avais pas la capacité de mesurer directement tout ça. Mais enfin, 340 nanomètres, ça passe. Donc, en fait, non, c'est un problème de caméra pour beaucoup, de temps de pause. Non, il y a un vrai potentiel. Après, je ne pense pas que tu l'as cité, mais c'est surtout la calibration. Enfin, tu as cité la calibration, en fait, hein, spectrale. Et puis, les problèmes de radiométrique aussi, c'est-à-dire avoir des lampes UV pour avoir le continuum et étalonner les données en flux, voilà, ou en relatif en tout cas. Voilà, c'est le problème. Donc, d'abord les caméras, plus l'UVEX en fait, et la calibration éventuellement.
Okay, so what Christian is saying is that clearly the main parameter, the main limit comes from the cameras. And by the way, the UV, the CMOS cameras, the ZWO camera, the cameras are very good in the blue parts. Some of them have a window in front of the sensor, which is made in silice, which is very transparent in the UV, and some other. There are some cameras with a standard glass which are not so transparent. So, but this is really mainly the sensor, the camera sensor, which is the limit. And the UVEX by itself could go further. But we have the problem of the flat lamp, so we don't have the continuum in the UV. So we should use UV lights, but it's something very complex to use. And we also have the question of the calibration. So we don't have a lot of calibration lamps to go so deep in the UV. Okay, but this is not really by structure. This is not really the UVX, which is the limit. Thank you, Christian. Any other question?
François, look at the chat because there are a long question from Tonis and another from John Coffin also.
Oh, I see that you have a recommendation, Tonis, regarding the calibration. When done like this, adding the selection of use comparison lines. Yeah, right. And the telegraphic noise. Well, I'm looking at your question, Tonis. We'll discuss that. I propose that we'll discuss that. We'll talk about the recommendations that we have to improve this calibration. Okay. Do the telescope optics affect the sensitivity of UVX in the UV? Well, yes, of course, yes. Well, anything on the light path is affecting the sensitivity of the UVX, and this is why we recommend for the UVX to have purely mirror telescopes to make sure that we have no chromatism. I've shown you that I'm using an RC8 Ritchie Chrétien 8-inch telescope. This is a new telescope for me. We bought it recently, really to be able to, so because the Ritchie Chrétien is one of the great architecture only based on mirrors, so it is purely achromatic, and this is something important. Yes, if you use, for instance, if you use a telescope lens or like a Takahashi or something like that, I'm sure that you will have almost nothing in the blue. Okay, so really the solution for this is to have a purely mirror telescope. So either Ritchie Chrétien or Cassegrain, which is f10 generally, or Newton, but the Newton is f4, f5, even f3 sometimes. So it's not really adapted for the UX. But if you have the choice, prefer a purely mirror telescope.
Tu peux dire effectivement que c'est l'aluminium pur où vous protéger, mais qui est le plus idéal en fait, ce que tu trouves dans tes Ritchie Chrétien. Mais que beaucoup de télescopes malheureusement sont optimisés avec des coatings qui optimisent, mais pour le visible uniquement, pour la partie visible du spectre, et c'est une catastrophe ou c'est très mauvais dans l'UV. Et donc voilà. Donc je voudrais aussi préciser que l'UVX peut travailler aussi dans l'infrarouge et qu'il y a une très bonne performance aussi.
Ouais. So what Christian is saying that's interesting. He says that there are two things in the telescopes and in the optics of the UX. So there is the coating by itself. So the best is to have a protected aluminium, which has the best efficiency. We have something like more than 90% reflection. But on top of that, we put an anti-reflection coating, a coating, and this coating is usually optimized for the visible range. And it happens that these coatings are really a problem when we go so far in the UV. Okay, so it's not only the reflection, but this is also the coating, the AR coating that we put on the different components. And we know for the UX, we did work with our suppliers to have really an extended coating. So it means that more layers in the coating, so a more complex and more expensive coating to improve the sensitivity in the blue. And Christian is also saying that. So I did only one observation, and I put the grating in the UV part, in the blue and UV part. But Christian said that Uvex also works perfectly in the visible and in the infrared range. So it's not limited to the UV, of course. So for me, the UV, what I've seen with this simple observation is totally new to me. But we also have a lot of things. When we compare to the ALPI spectrum, we will double the wavelength cover that we cover with the Uvex. It's just incredible. Okay. I continue with the questions. Is it interesting to remove the glass in the front of the parts of the camera to improve detectivity on the UV part of the spectrum? Good question. So Christian said that on some cameras, some ZWO cameras already have a few silica window, which are very good. But you did some tests, Christian, by replacing the window of the camera. Generally speaking, it's dangerous to remove it, purely remove it, because you have to protect your sensor against the dust and so on. But it can be one of the limitations. Yeah. Tony, I've used a very bright mercury Gessner tube with a printed Uvex 3, and I think have lines lower than 300 angstroms, 3000 angstroms. Is that possible? Wow. Christian, you know?
Est-ce qu'il y a des longueurs d'onde plus courtes?
En fait, ce que dit Tony, c'est qu'avec il a utilisé un télescope, un tube Mercury Gessner, et avec son Uvex en impression 3D, là, il pense qu'il a vu des lignes en dessous de 3000.
3000. Mais quelle caméra il utilise?
Which camera did you use, Tony? Can you tell us?
Hi, François. Yeah, I used an attic and I removed the front window.
Okay, you remove it totally.
Yeah.
Okay.
Okay.
And which attic? Which model?
460.
460. Okay.
Ok. Non, les CCD sont très bons, hein, des fois, en fait, effectivement. Et donc, ça peut être.
So, maybe.
Maybe. Et ça confirme ce que je disais, hein, c'est-à-dire que c'est pas Uvex qui limite, du tout.
Yeah.
Mais c'est vraiment la détection. Voilà. Donc, les précautions qu'on prend. Et puis, il faut avoir des stimuli aussi. Voilà.
Okay, so what Christian is saying, Tony, is that, well, maybe it is impressive, but it is possible. And this confirms that the limit does not come from Uvex itself, but it comes from everything around. And yes,
faut se rappeler que quand même le meilleur filtre, c'est l'atmosphère quand même terrestre qui coupe à 330 donc, nanomètres.
Yes.
Et donc l'ozone coupe autour d'eux. Et donc effectivement, malheureusement, c'est souvent le blocage qu'on a. Dommage, on ne va pas dans l'espace avec Uvex pour l'instant. Voilà.
C'est 330, tu dis?
Oui, 320, allez, 320.
Okay, so Christian says, well, we still have one problem at 320 or 330 nanometers is that we are totally filtered by the atmosphere. So if your observation, Tony, was a star observation.
Non, mais c'était en fait, lui, il a observé avec une lampe au mercure.
Une lampe, il n'y a pas de problème.
Okay.
Avec
So
la lampe au mercure,
okay. Oh, okay, bright mercury Gessner. Okay. Okay, so the mercury was the lamp, was not the telescope. Sorry. Okay. So then in this case, it is possible, Tony, that it is possible that you get something below 3000 angstroms. But you will never have that with a star because of the atmosphere.
Yeah. Okay. I'll send you the FITS file.
Okay. Wonderful. Thank you. The Uvex has it been tested with a Cassegrain or a Muon? And Cassegrain, I think that you did it, Christian. Oh no, you did hesitate. You think it is a good solution? Well, it is a good solution because it is a purely mirror structure, and it is an f10 telescope. So again, if you have faster telescope, slower telescope, you will have a better quality. But the problem is that you will extend the focal length, of course, and then you will extend the star size at the focus. Well, this is always the same question. But to my knowledge, I don't think that it has been tested, but it should be work perfectly with a cast grain at least. Okay. Okay. So and you have a question, a reply from Vincent. Okay. Any comments? Any reaction? Any?
I wanted.
Sorry. Go ahead.
I just going to say, Francois, I'm excited.
Thank you, Sean. I'm also, and this is really the beginning, and this is a great instrument, and the structure of the instrument is great. It's interesting, and I think that's the declination we have made, mechanically speaking, it's really a pleasant instrument. So I'm impatient that you all receive yours, and we work on real observations. Thank you, Sean.
Come on, Gary, you have a question.
Not so much a question as a comment. I noticed a little bit of sensitivity to CMOS cameras in some of the questions before. And while I'm a newbie in spectra, I have about 50,000 observations of variable stars photometrically taken with CMOS camera over the last 3+ years. And I have another 20 years of CCD photometry that I've taken over the last 20+ years. And I can tell you unequivocally that the CMOS cameras, they are better. I get about 2 to 3 times lower error bars in my light curves using CMOS cameras. And there's another thing which might address the telegraphic noise, and that's a stack on the fly feature that we use, and where we take about 6 images instead of a single image and stack it in the camera. So I wouldn't fear the CMOS cameras. They are a little different. They do have different quirks, but they definitely perform. And so don't worry.
Yeah,
that is assuming that they work as well in spectroscopy as they do in photometry.
Yeah, this is the same. You are so very interesting. Thank you for your comment. There is something which is important. You are saying that you can filter the telegraphic noise by doing a series of images instead of taking only one. So I agree, and I especially agree when you are doing imaging, because when you are doing imaging, all the images are exactly the same. When you are doing spectroscopy, if the problem is that if you, for instance, if the star is moving in the slit, so the tracking is not perfect, then from one image to the next one, you may have quite different levels of signal at the same position, and it can be confused with the telegraphic noise. You know what I mean? So when you are doing imaging, all the successive images are really comparable. They have the same level, and you can do a medium or an average, a median or an average, and eliminate the extreme pixels. It is not that simple in spectroscopy, but well, this is always the same idea, but it's not that simple, and really not because of the kind of observation, but simply because the kind of images that we are making are slightly different, and then we cannot use exactly the same data processing. And oh yes, the question about the motorization, I did tell you at the beginning that I will show you something, and I didn't do it. Just to finish, I will. Okay, you wanted to add something, Gary? No. No. Okay. I'm switching to the again. to the system. And maybe so we are doing that. So for regarding the motorization, so for the moment we are really focused on the production and the manufacturing of the UVEX, but we are already working on the next step, which is the motorization. And this is just to show you that we have made some 3D printed part. So in this case, for the grating angle, we have designed this system, and so this is really to explore and to check how it works, to check the if the motors are strong enough, is the solution is precise enough, and so on. So it is not the shape of the final solution, of course, but this is the idea. And for the focus, we have a small, in the two cases, we have the same stepper motor, and we have a belt here in this case, and we just have a gear in this case to have enough precision. And so this is what we are doing. I know that you guys from the nice people and the UVEX team, you are doing designing some solution also for the UVEX 4, if I'm right. And maybe you can tell us what you are doing. And by the way, I also have the electronics. So I do have an electronic board with a small Arduino, as we like. And this is I'm working currently on the software development of this card to control the stepper motors. So this is where we are, and I hope that we have a final solution soon. And by the way, this is very, very interesting to have the 3D printing to do some quick prototyping and test solutions. And this is a wonderful tool. Maybe Pierre, or I don't know, Jean-Luc, or if you want to add something.
Oui, tu as une question particulière par rapport à UVEX 4?
Oui, c'est-à-dire, je sais que vous êtes, enfin, j'ai entendu que vous étiez en train de bosser sur sur la même question de la motorisation.
Ouais. Nous, on a pratiquement finalisé la motorisation. Jean-Luc Martin vient de terminer le driver SCOM en plus. Donc, normalement, il reste encore à faire quelques essais, mais on arrive à pointer le champ du spectre facilement maintenant, sans problème.
Okay. So, well, Pierre is part of the team of the UVEX, the team who is working with Christian of the UVEX project, the general UVEX project with the 3D printing solutions. And he says that yes, they have almost finished the design of their solution with for the UVEX 4, which is the next generation. And Jean-Luc Martin has finished or almost finished the ASCOM driver.
Okay. Et c'est fait avec les cartes Arduino aussi, pareil. Hein.
Ok. Il y a un truc que je me disais, peut-être qu'il faudrait, ce serait peut-être pas compte d'aller se concerter sur les protocoles de communication là, pour qu'on ait des trucs qui se ressemblent, qui soient réutilisables.
Ouais, c'est la partie la plus délicate en fait.
Ouais, mais ça vaut peut-être le coup qu'on discute pour voir.
Bien sûr.
Ça marche. I'm saying that maybe we would have to discuss about the protocol to see if it's possible to have the same protocols and to reuse as much as possible what we are doing. Okay. That's it. So we have passed over 2 hours. It's too long. I'm sorry. Olivier?
Nothing else. I think there are no more questions.
No more questions. Good. Thank you. Thank you for your participation. Thank you for all your questions. And thank you for all the observations that you will do soon. and again, tell us when you have any news, and we do our best to send you your UVEX as soon as possible. Thank you.